on the image.
Giovanni Pederiva, can you share your screen?
Yes. Can you hear me?
Yeah.
Okay. Okay.
Okay, just a second here. If I know to do it. Oop. Okay, so Giovanni Pederiva, that we talk about machine learning for hadron correlators from Lattice QCD. Thank you, Giovanni.
Thank you, everyone. Thank you for coming to this workshop, and thank you for the organizer for giving me the opportunity to present this work that I've been doing with my advisor, Andrea Schindler, in the past couple of years at Michigan State University. So I'm actually very glad to be able to present this work after Borham's presentation, because this work we started actually was inspired by by his work when he came and presented it at Michigan State 3 years ago, I think it was. So many of the things are taken from sort of the same formalism, and also, but the key idea behind it is slightly different. So I'm not going to give an introduction to Lattice QCD, as we already had it and in the previous talks, and also we're running a bit late on time, so I'll just point out to the main things, which are the main observable we'll be looking at are 2-point correlators, and they are an important observable, and they can be interpreted via spectral decomposition, and they allow us to look at the states of several hadrons on the lattice. And they come from taking interpolating operators with the proper quantum numbers on the lattice, and one then performs the contractions of such interpolating operators, and in doing so we end up with these terms down here, and these are the crucial things because they are the quark propagators. And for a generic term Q, in order to compute the quark propagator, we need to solve an inverse problem. So D is the Dirac operator, and its structure depends on the lattice action that one is choosing. And we need the inverse of the propagator, and in principle that requires inverting a very large matrix. However, if you set a source, in this example here, we can set a point-like source. We can reformulate the problem in this way, so that now we only have to compute just one column of the inverse matrix. The way we solve this problem is effectively a linear system. So we have a set of linear systems for every quark, and the fact we have a set just comes from the fact that we are interested in all the color and Dirac structure of these objects. And the matrix is a very sparse one. We deal with numerical methods that come from sparse linear algebra, and its exact form depends on what action we're using, but in most of our calculations we use just Clover fermions. And it's important to know that we have such linear system for every quark flavor in our problem, which means that these calculations are what takes the most time when doing measurements on in Lattice QCD. The way we solve these linear systems is through iterative solvers. We use, for example, the simplest methods are conjugate gradient solvers or its variations. In this work, we use the PCG stabilized algorithm. And this class of algorithm all have a key feature, which is you iteratively solve the linear system, and at every step you compare the current solution against some and against the right-hand side vector, and you compare whether the difference is smaller than a fixed stopping parameter epsilon, which basically describes the precision with which you want your final result to be. So the goal of this work and the main idea behind it is to try to accelerate the calculation of these linear system to get the core propagator and in the end core hadron correlators by using numerical data coming from different stopping parameter epsilon. So the idea is, instead of calculating the propagator with a very small value of epsilon, so a very precise determination of the linear system, we only calculate a very high system on a subset, the high precision solution on a subset of a total lattice, total ensemble of gauge fields. And we compute only a very low precision solution on the rest of the ensemble. And by doing that, we are effectively saving some computational time. And then we try to use machine learning to map the low precision solutions to the high precision ones. In order to make this unbiased and improve the results, we used a very similar bias correction technique to the one that we've seen in the previous talk. So I'm not going to go into too much detail there. Here are the gauge fields properties that the ensemble properties that for the ensembles used in this work. These are all Clover fermion ensembles, and we see we have different masses in the ranging from 400 to 700 MeV, and lattice spacing on the order of 0.1 Fermi. So here is the motivation, the actual motivation why we think this can be an interesting solution, is that we see from our calculation, we see that the time to solution for the linear system is roughly linear with the log of the stopping parameter epsilon. And we can see it both on the average time to solution on the ensemble configurations. We see that it grows, seem to be growing linearly with the log of the stopping parameter. And these calculations have to be done, obviously having the same computational setup, otherwise these wouldn't be fair comparisons. But also if we take just one configuration at random and we observe the solver history, so like the residue at every iteration of the solver, we see that this behavior is seen to be linear with the log of the residue. So the idea is to pay this price, or the price of the very large, very high precision calculation only on a subset of our statistical ensemble. And then on the rest of the ensemble, just pay a small price and use machine learning to basically improve our low precision results. This obviously can only be done if there is some correlation between the precise and sloppy data. And we see that there actually is some very strong correlation. Here we see it for some different hadron species. For example, for the pion, this correlation is very strong throughout the sourcing. Here on the x-axis, we have the sourcing separation. We see that for the pion, this correlation is always very strong. For the proton, for example, this correlation gets slightly worse towards the center of the lattice, but I mean, that is mostly expected because in this region, there's basically no signal, it's only just noise. So in the region where this could be useful is before this becomes complete noise dominated. So here's an example of the raw data that we're using. This is with the pion correlator. This is very smooth because it's a meson, so it's symmetric in Euclidean time and positive definite. But the key idea is we're trying to find a way to map these points, these low precision points, to the high precision ones, which are the blue ones. They're a bit hard to see, but they're so we're trying to find some mapping between these values. So the way we do it is to we have two different approaches. One is to do it point by point, so looking at one sourcing separation at a time, and this is what we call the single point neural networks. And so since we have no idea a priori of what the functional form should be for this mapping, we just allow any mapping by using a very small but very expressive neural network. And so in the simplest case, we provide 2 or 3 precisions as input. These are very low precisions. So it means that epsilon 10 to the minus 1 just means that the residue is below 0.1, which is actually a very imprecise calculation, but we will see this actually gives some decent results. But so we use low precisions and a target 10 to the minus 8. So we allow any function, so we let the neural network approximate whatever function it needs to do. But then we can also use a more refined approach. So maybe there's also correlations between neighboring points. So the data, how it behaves at one sourcing separation time can also be affected, not be affected, but be correlated to what's happening at the neighboring sourcing separations. And that also, this obviously makes sense because the linear systems are very similar in that sense. With respect to that, the only thing that is changing is the right hand, is the source, and the source is just shifted by 1 effectively. And so the gauge field is the same, and so there's no reason to expect that the result shouldn't be correlated. So in this case, we provide different precisions, only the 2 smallest precision, and but also data regarding the t-1 and t+1 as input. And again, we have this neural network, and we let it basically approximate the function, which we have no idea what that should be. Then the other approach is more radical, and that is just trying to learn the high precision correlator all at once. So as inputs, we use the correlator at 1 precision, or 2 or 3 precisions on all for all t's, and as output we expect the correlator at all t's as well. And now this should be noted that while these neural networks are rather small, the global one obviously are much larger. For example, in the input layer here, it's on the order of 100 points, while before it was just on the order of 10. And the output layer is on the order of the temporal extent of our lattice. So this requires a lot more training, and it is potentially less effective because the number of gauge fields that we have is on the order of 1,000. So trying to train a neural network with a very small input size, very small data sample can be hard, especially if the network is large. So in order to assess the quality of our results, we computed 3 quantities. Let's start from the second one. So we calculate the ratio of the variances between our machine learning estimate and the full and the expected variance, which we estimate by just performing a regular calculation with high precision over the whole ensemble. We calculate the compatibility of our results, that is the different distance weighted by the standard deviation between our machine learning estimate and the exact result. And we also compute this gamma factor, which is the computational gain. So it's how much computer time basically we are saving by using our machine learning procedure compared to doing a full high precision calculation. So this is the ratio of the times it takes to calculate to calculate the correlator with a low precision over the high precision, scaled by the fraction of configurations on which we are not calculating the high precision data, plus the fraction which we're actually using. We're calculating both because we need it for training. Here F is the training fraction. Okay, and here are the results for the different methods. Here I'm going to show for 3 different scenarios. One is very small sourcing separation time. One is an asymptotic, where we expect the effective mass to plateau. So here we have excited states, and in principle we don't. And we also calculated on a derived quantity, so the effective mass of the system, of the hadron we're looking at. So these results are for the pion, and we see that all the methods seem to perform very well. So the expected variance is, so the ratio of the variances is always around 1, which means we're not really losing much in terms of accuracy of our results. This variance ratio is growing with the training fraction, and this also makes sense because we're effectively having less and less statistics for the determination of our correlators, the larger the training fraction, because we're using more data to train the model, and then we actually have less statistics on our final estimation. However, we would also expect to have very large variance ratio for small training fractions, which we don't see. And that is implying that we actually need very little data in order to be training effectively these neural networks. Here's the compatibility of our results. So if we take the difference between the central value and we scale it by the standard, by the combined error, then we see that it's always well below 1, which means that we're not changing our data, which also is very good. I mean, it's not only predicting the right uncertainty, but it's also predicting compatible results. So this seems to be a solid indication that we can use this method. And here we see the first caveat that if we have very little training, then this is not really, if the training fraction is very small, then this is not really working properly. So it may be safer to use slightly larger training fraction than what we can just guess from looking at the variance plots. And here is the product of the variance ratio the inverse product of the variance ratio times the gamma factor, so the computational time gain. And this is effectively saying how much time we're gaining. So anything which is more than 1 is a gain, and we see that these curves are all well above 1. So it means by using this machine learning procedure, we are saving computational time at the expense of some precision, but the balance between the precision loss and the computational gain is always positive. And you see that this factor is around 2 or 3 in the region of 10 or 15% training fraction of the ensemble. So here it's this spike here is hard to say. It's probably a fluctuation based on the structure of the ensemble we used, like the original data of the ensemble. But so we can also see some difference between, this is obviously expected, between the methods that use a higher epsilon, a smaller epsilon. So these two curves use data that's calculated with a stopping criteria of 10 to the minus 3, while all the other ones only use 10 to the minus 1 and 10 to the minus 2. So these two are more expensive. So when we weight them, the gamma factor for these two curves is smaller. So that's why there's this clear separation between the methods that use 10 to the minus 3 data. So what we can conclude from this is that we do achieve a 2.5 speed up consistently in this pion mass range from 400 to 700 MeV. And with these, for all the ensembles, we can observe this. And so we're quite confident that this works in this mass regime at these lattice spacing with Clover fermions. The overall method seems to be solid and it produces good results in all the cases we tested it. We want to work a little bit more on defining a solid operative procedure because from the results I've shown you before, maybe some, for example, in different regions, it might seem that single point neural networks work better, but in some others, it also makes more sense to use the nearest neighbor, the ones that also take into account the nearest neighbor points. So we want to maybe find a clear cut where one model is better than the others and maybe come up with a more precise recipe. And we're also testing this in partially quenched cases. So trying this for heavier quarks because we think that there's more potential for larger gains when we go to higher masses. And for those systems, the numerical precision of the solver is critical. And so calculations become more and more complicated because they have to be done in quadruple precision. And so maybe this method can be effective and lead to a larger gain in such cases. And with that, I think I'm done.
Thank you, Giovanni. So, questions? Yeah, but okay, Thomas, please go ahead.
Yes, can you hear me?
Yes.
Yeah. Perfect. Yeah, very nice talk, Giovanni. Thank you very much. I had a couple questions. It seems you applied your networks predominantly to pion propagators, and the correlators for the pions, because of the opposite parity states or degenerates over it, they're symmetric, right, around the midpoint. Is there a way to constrain your network to respect this symmetry, or do you just expect the network to learn this symmetry in some manner?
That's a good question. No, we've not implemented this symmetry per se. So yeah, so this, okay. So when we take one, when we clear in time at the time, it's not really necessary because we're only looking at one point. But in this case, when we try to learn the whole correlator at once, that could be effective. And no, we're not. We don't impose any constraint.
I thought perhaps you might, for example, fold the correlators.
Yeah,
first.
I was just thinking, yeah, if we provide the unfolded correlator as input, but we train based on the folded high precision one, then that would somewhat impose some symmetry in this.
Right. It's really only specific to the pions, right? Other systems would not be the case. So my other question was, so you say you got factor of 2.5 speed up for various ranges of M-pi and lattice spacing. Now, if I understand right, for each M-pi and for each lattice spacing and for each temporal and spatial volume extent, you will have a separate model neural network, or is there one master neural network that can work for all of this?
They're all different, yeah. So the idea is, I mean, training these neural networks is rather fast. So these neural networks have the order of 100 or 200 nodes. And these is probably already an overkill because the input layers and the output layers are very small. So it's just a conservative approach to make sure that it can, in principle, approximate any function that maps the data. The global methods are slightly larger, but they are comparatively speaking, it's still a small neural network compared to other types of problems. So this training is very fast. It takes minutes.
Right.
So it's realistic to think that you can just train these neural networks on the go for every different sample. It's not expensive in that regard, especially considering that the measurements, I mean, take hundreds of thousands or millions of core hours on HPC facilities, and this takes a couple of minutes on a laptop. So
yeah,
we completely neglect the training while making considerations for the timings.
How deep did you go in the layers?
Oh, we found that 3 layers is fine.
Okay.
So these networks are rather small.
Right.
Yeah.
Okay. Okay. Thank you very much.
Hi, Giovanni. Many thanks for the talk. I have also a couple of questions. One is the sensitivity of the data that you have reported about the speed up on the size of the training sample.
Mm-hmm.
So, I mean, you know, have you tried to vary the training sample, and how does it affect the precision and the speed up that you get, you know, by increasing the training sample?
Yeah,
I understand.
These are the, it's basically what we're showing in these plots. So
Yeah.
here we have a fixed sample. So our samples are rather small. They're on the order of 500 configurations each. Mm-hmm. And now, basically, we set this is the training fraction of gauge configurations in that ensemble. So it goes from anywhere from 5% to 40% of the gauge configurations used for training volume.
Okay, thanks for going back to that. The other question that I had was, I mean, you know, you comment that the solution is lower precision. Can you put it back in your inverter and obtain one that is of comparable precision? I mean, how long will it take? Or if you wish, the flip side of the question is to obtain a solution with similar precision, how long would you need to run the inverter for?
Oh, okay. For the first question, this cannot be done at, I mean, we plan to do that, but it's a much harder problem because these results are for the correlator, which is the contracted propagator. So we have no knowledge of the propagator after the machine learning procedure. Yeah. So we cannot just put it back in the inverter. So no, we cannot do that. If we go one step deeper, so try to do some machine learning fitting at the level of the propagator, then yes, that could be done. But it's not what we're doing here. We're interested in trying whether that's feasible or not, but no, we don't. For your second question, that is, maybe I should have stressed this a bit more. That is, you can see it here. I mean, getting a high precision solution, the actual cost comes from here. I mean, this is the thing. We always know that we can get numerically, we can get the exact high precision solution because we just let the solver run for longer. But that takes, I mean, it's a matter of stopping your solver when you're around here instead of going all the way down here. So you're effectively saving a lot of iterations in the solver. In terms of time, I mean, it's
Yeah, let me clarify this part of the question. I mean, so the precision of the propagator that you get out, if I understand correctly, is lower in some sense. So if you are aiming to the same level of precision with the conjugated gradient or whatever method, I mean, how much time would you save there? I want to understand better this factor of 2.5.
Oh, okay. So you say if I wanted the same exact precision.
Yes, yes, more well,
okay.
Okay.
Okay, so it's inverted question. Okay, yeah. So if I want the same precision, then well, the key idea is, well, you can't. I mean, by doing this, we see it from here, right? You always get slightly larger errors. So, but on the flip side, one could say, well, if I am saving, if all my results are I don't know, have a variance which is 1.2 or 3 times larger than my fully precise data, but then I'm saving a factor 2 in calculating these correlators in the first place, then I can just spend more time calculating more lower precise correlators. And then by increasing the statistics, I can get down to a similar level of my final estimator in terms of precision.
Okay, thank you very much. Thanks a lot.
Are there other questions? I don't see any. So we thank Giovanni again.